So this type of question, it starts off by saying 1 mark is available for the quality of spelling, punctuation and grammar, and that's worth the 1 mark there. So for that you need to use keywords, you need to use complete sentences. When I go through this personally now, I'm just going to write out the bullet points and I'll let you make them sentences yourself. The question says, phenol reacts much more readily with bromine than benzene does. Describe with the aid of a diagram the bonding in benzene. Explain why electrophiles, such as bromine, react much more readily with phenol than with benzene. So we're going to start by taking a bit to describe with the aid of a diagram the bonding of benzene, and we're going to do it here. So the bonding in benzene is, remember we have our 6-membered carbon hexagon ring there, and we have p orbitals extend above and below the plane, above and below the plane, above and below the plane, above and below the plane. And I will put these as p orbitals. And then what happens, remember, is the p orbitals overlap. And what we find is the carbon skeleton stays exactly the same, but we get a high cloud of delocalized electrons above and below the ring. So we're going to make a note of that. So that's pi cloud or pi orbitals above and below the ring, and then that there are delocalized electrons. What else can we say? Well, if we look at the way the carbon-carbon atoms are linked together, the carbon-carbon bonds are all the same length, and they are intermediate halfway between a carbon-carbon double bond and a carbon-carbon single bond. So they're not quite a carbon-carbon double bond, but they're not quite a carbon-carbon single bond. Carbon-carbon bond. I can say the bond angles in the ring are all 120 degrees. That's that bit finished with. Then it says, explain why electrophiles such as bromine react much more readily with phenol than with benzene. So if we look at the structure of benzene compared with phenol, benzene is that compound there, C6H6, but phenol has got an extra OH on it. Remember, there are 2 sets of lone pairs on the phenol. Let me put it there. So the reactivity of phenol is more reactive, and the difference is between benzene is because benzene doesn't have an OH there, it doesn't have an oxygen atom, it doesn't have specifically the oxygen lone pairs that phenol does. So we say in phenol, what can we say? We say the ring is activated. And what we mean by that is because the lone pairs from the oxygen are delocalized into the ring. So those lone pairs there get sucked into the ring, and the oxygen are delocalized into the ring. Delocalized into the ring. What does that mean? It means there's a greater electron density in the phenol molecule than there is in benzene. So there's greater electron density in phenol. And if there's a greater electron density, what does that do to the electrophile? Well, it means there's a greater induced dipole in the electrophile when you're using phenol compared with when you're using benzene. So greater induced dipole in the electrophile. Why is that? Well, the reason is that those said there the lone pairs in the oxygen get sucked into the benzene ring. That means there's a great electron density. It polarizes the electrophile more readily than it does with benzene, which means phenols reacts more readily with an electrophile than benzene does.